So, hello. Um, so this the Lilian transformation. So first of all, why we need new transformations or new equation to interpret the motion and these things. So we have a problem here that Michelson and Morley experiment failed, and they didn't prove that there's uh, any difference in interference pattern. So what they was need to prove, or what they need to get out of this experiment, that the the velocity of Earth relative to the ether frame, and the direction of the velocity too. But they didn't prove that. So when they got this result, there's someone called Lorentz. I don't know what's the first name, but he's called Lorentz. So he came out with an idea or some ad hoc principle that you know, when you got the result, you have the final result, and but your equations is not there's something wrong in your equation, so you are starting to manipulate your equation to agree with the result. This actually what Lorentz have done. He got these equations, but these equations are agreed with the result that Michelson and Morley had, but he didn't know the physics beyond these equations. He just got the equation. So that's why we call this transformation Lorentz transformation. But when Einstein came and he interpreted to us what is physics beyond this equation, so I think it should be named Einstein transformation. But anyway, Lorentz he came with it first, so fair enough. So let's move it. Here we know that x dash, y dash, z dash, t dash. So let's begin with this first. So we have two frames here, sigma dash and sigma. So and this sigma dash moving to the right relative to sigma frame. So we need to get x dash, y dash, z dash, t dash. So this is the result that we will get by the end of this video. So we know that x dash it should be a function phi 1 or a function in x, y, z, t, and the same for y dash, z dash, and t dash. But we need to get the function. So this is what we prove right now, or what we do right now. So here's Einstein. So Einstein came with these two principles of special relativity. The first one: all physics laws have same form in all inertial frames. So and the second one, the speed of light is constant in all inertial frames. So for the second principle, actually you can get the second principle from the first one, as from where we got this constant speed of light, from Maxwell equations. So Maxwell equations, we can consider it as physics law. So when Maxwell equation said that light has constant speed of light, but Maxwell equation was on the Earth. So this is from the frame of reference of Earth. So this is a physics law. So it's happening in Earth, so it can be valid for all frames. So as long as it's constant here on Earth, so it can be constant in all inertial frames. So this is how we can get the second principle from the first one. So Here during this transformation we are talking about a moment when O, which is an origin of this sigma frame, comes on top of O dash, which is an origin of sigma dash frame at the moment t equals 0, t equal t dash equals 0. So we consider when O came on top of O dash, we are measuring time at this moment is 0. So, and x equal x dash equals 0. So fair enough, because both origin are on top of each other. And y1 dash equals 0, z and z dash equals 0. So this light pulse, we got a light pulse here. And open the shutter and close it, and we get a light pulse reach a point P in space. So the coordinate of this point in sigma, it has x, y, z, t in sigma, and this point has also x dash, y dash, z dash, t dash in sigma dash, in the frame sigma dash. So this light pulse, the distance that this light pulse passed from the origin to the point P, we can calculate it by this equation, because the speed of light is constant. So we can. This is our components of the motion, x and x, y, z direction. So this is the speed of light, c, and t is time. So c and velocity multiplied by time, we got here the distance. So this is in frame sigma, and when we are talking about frame sigma dash, here's the same. So we can simplify it, and these were squared both sides, and this is what we got here. So this is what we called B equations, because I will refer in this video the B equations. So B, it's a this is from the principle to that speed of light is constant. So now we will use the first principle. This first principle, all physics law have the same form in all inertial frames, to prove that this function phi 1, phi 2, phi 3, phi 4 must be linear in x, y, z, t. So why we need to prove the linearity here? Let's we'll explain it by the law of inertia. So we have here a free particle in the frame sigma. So as long as it's a free particle, so it's moving in constant speed. So this is ux constant, y, uy, uz are constant. All of these components of the velocity are constant because it's a free particle, so it's moving at constant speed. So as long as this is the case in the frame sigma, which is a free particle, and these velocity components are constant, so it will be the same in the frame sigma dash. So this particle will be also a free particle, yeah, in the frame sigma dash. So this means that the velocity components in sigma dash are also constant. Ux u dash x, u dash y, u dash z. So all of these are constant. So here that free particle is moving in x direction. This free particle is moving in x direction. So when we are talking about frame sigma dx, which is the distance, and in dt, here dy and dz equals 0. So it's okay because it's only moving in x direction. So when we consider this free particle motion in the frame sigma dash, so what we got here, dx dash dt dash, we will calculate. So from where we got this, so as I state here, x dash, and here's t dash, y and z here in the situation that we are talking about right now, x dash and z dash are equal to 0. So x dash, y dash and z dash equals 0, sorry. So only x dash t dash we have value for it. So x dash must be equal to function in x, y, and z t, but we do not know the rate of change of x, y, z, t. So in this case, we will use multivariable differentiation. So when we apply multivariable differentiation, here we got d phi 1 over dx multiplied by dx, and so on, and the same for dt dash. So by substituting dy and dz, because r equals 0, so we'll put dy here, here, and here equals 0, and so these four terms, we'll get rid of these four terms. So here's the new equation, and by dividing this equation by dt dash, so here we got this equation only by dividing dt. So when we divide dt here, it will dx over dt, which is a velocity here. Dx distance, dt is the change of time. So we got ux and dt over dt. So gone. Dt over dt the same. Dx over dt will lead to ux. And here is the equation that we are talking about right now. So u dash x equal this equation. So because this is a free particle in sigma, in the frame sigma, this means that ux, which is a velocity component in x direction, is constant because it's a free particle, as we mentioned before. And by applying the first principle, we got that u dash x must be also constant, because all physics law have the same, yeah, the first principle. So, but in order to be constant, this u dash x to be constant, we must have these terms, d phi over dx and d phi over dt and d phi 4 over dx and d phi 4 over dt. These terms must be constant. Or in another way to say it, these for phi 1, this function phi 1 must be linear in x, and phi 4 must be linear in x. Phi 1 must be linear in t. Phi 4 must be linear in t, in order to have this constant, and these are also constant. So it's both. In order to have both of them are constant, these should be constant. So we know that ux is constant, but we want to prove it mathematically that we need this also to be constant. So in order to achieve this criteria, we need these terms to be constant, or this function must be linear in x and t. So so what we got, we named these terms by constant a, b, c. C is here is a constant, not the speed of light, it's just constant, and d. So before moving to the other thing, so if you had a look on special relativity, the original paper that I've sent you, you were surprised that Einstein didn't get the linearity by applying the law of inertia, but he got the linearity from something called the homogeneity of space-time. So we have a system here, is space-time, and it's homogeneous. So hopefully you watched the video that I sent you about homogeneous and linear system. So when we are talking about here, yeah, you got the linearity from this part. So we are talking right now when dx, dy, dz, dt equal to some certain value. So we should get dx dash get some certain value without considering the beginning of this dx, dy, and d. So without considering this rate of change, you know. So because these values dx, dy, dz, dt equal to some certain values, and so we need to get dx dash also equal to the same to the same value whenever we started the equation, or what is the beginning of the distance, or what's the beginning of time. We don't know. We don't care about the rate of change. We only need this value to be constant. So this means that we are need this d phi 1 over dx, d phi 1 over dy, d phi 1 over dz, d phi 1 over dt. These terms must be linear, or this function must be linear here, in order to not affect our value. So we need to get the same value whenever we start the experiment. So he got the linearity from here. So if you are a little bit confused about this, the definition of linearity that Einstein get from this equation, so it's okay. You can just follow the flow of idea that we prove the linearity by the law of inertia. So it's just okay. So after we are here right now that these terms must be constant. So here's a point that these terms is a constant in our experiment, but it might be a function in velocity, in the relative velocity. So here that we are talking right now that two frames sigma and sigma dash are moving relative to each other. So and this relative velocity is constant. So these terms might be function in this velocity. So, but we don't care. We are just care about there is no change in the coordinates of this term of the coordinates. So coordinates are the same. So this is what we are need here. So after we name this constant a, b, c, d, we're substituting here in this equation, and by integrating the u1 u dash. That is what we get here. These e and e dash, e double dash, e triple dash, all these are integration constant. We will get rid of them right now. So here now we are doing that we're talking at a certain moment when O, which is an origin of frame sigma, came on top of O dash, which is an origin of frame sigma dash. So here at this moment, x dash z dash plane is xz plane. So the same for xy xy plane and x dash y dash plane. So here in xd and x dash z dash plane is xz plane. So we got that y equal y dash equals 0, and here for xy and x dash y dash plane, z equals 0 and z dash equals 0. So here any event having in xz plane is happening in x dash z dash plane in frame sigma dash. So at this moment, as I mentioned in the first page here, that at this moment x equals 0, y equals 0, z equals 0, t equals 0, because we are on the origin right now. So this event is happening on in the origin of these two frames. So all these values must be equal 0. But in order to be satisfied, this 0 to be satisfied, we need this integration constant to equal 0. So what we got right now, we applied this case we are doing when x dash y dash d dash t dash equals 0. So this constant must be equal 0. So after we get rid of this integration constant, we get this here, and because this free particle is only moving in x direction, so y dash z dash equals 0. So by applying this, we got here that a dash x plus because y equals 0 2, and this term, get rid of this term, z dash z d dash t. So for any x, z, and t. And so what we got from here, because this one equals 0, so a dash, c dash, d dash, all of them are equal 0. So what we will get here is that y dash equal this constant b dash multiplied by y, but y here we consider it is as a function of relative velocity. So this is just to be more precise, but we will explain it right now. So this velocity is, we have one thing constant here in this experiment, which is the relative velocity between two frames. So it might, we know that this b is constant, so in this experiment, but it might be a function in the relative velocity, which is, we're not care, but it might be a function in the velocity. So just to ensure we get it here. So and by applying the first principle, all physics laws are same in all frames. So what we get here in y dash, it must be applied here in y, and z dash must be applied in z. So here in y dash, y we are get here minus v and here v, because when we are talking that from the Galilean transformation, you will get that when this frame moving to the right, when sigma frame moving to the, sorry, when sigma dash frame moving to the right from its point of view, but from the point of view of frame sigma, it's moving to the left. So, and vice versa. So here we got v, and here we got minus v. So here's what we got, minus v and v. So by substituting this y by its value here, we will get this. So right now we get y dash in both sides. So this means that this term equal 1. And the same for z dash, we'll get the z here and not substitute here. We get z dash in both sides. So this term must equal 1. So what we need here, that the limit of this function b dash when v or c goes 0, or v goes 0, must be equal 1, and the limit c double dash v when your c goes 0 must be equal 1. And when we multiply this this function by v, and function of v multiplied by the function of minus v, we got 1, and the same for z. So right now we need a function when multiplied by itself by minus v and v, we got 1, and we will, when we take the limit of this function as v over c goes to 0, we got 1. So there is only one function is valid here, which is an exponential function. So you can try it, yeah. Multiply e square to minus alpha v multiplied by e multiplied by alpha v, which will lead to 1, and when we will take the limit when v of c goes to 0, we will also equal to 1. So here, you might say that we are just said before that these are constant and these are linear function. So why we are right now say that this equal to exponential function. So we are saying that this is sorry, I paused the video and pick back. So as I was saying, you might say that we say that this function b dash must be a linear function, but why we are saying right now that's in an exponential function. So this is a linear function in x, y, and z, but what happened here is that we figured out that it is exponential function in v, which we don't care. We just care about the coordinates x, y, and z. So it's linear in in x, y, z, but as you see here, it's exponential in v, and we don't care. And here's alpha and beta are just constant, so in our experiment, and we will get their values right now. So here's some confusion. Sorry, I will send you a message in WhatsApp too. Here it should be limit when v goes to 0, not v over c. So when v over, so we choose exponential function because of these two just these two factors. We need when multiplied by v and v minus v equal 1, and when we will take a limit of this function b when v goes to 0, v not v over c. This is just so v goes to 0 equal 1. So we choose here an exponential function, and this is an exponential function in v, but it's a linear function in x and y and z in coordinates. So we don't care. I will repeat again. We don't care about it in v. We just care that this is a linear function in x, y, and z. So this is what we got so far, that y dash z dash is independent of x and t. So this means that x and t are independent of y dash t dash. So another error here. It must be x and 2 independent of y dash z dash. So here is another. So you got it. So yeah, this should be y dash z dash. Here is when we are considering math is speaking here that when this independent of this, so we can say that we reverse it, and we can say this is independent of these two. So this should be y dash z dash. So and by using the first principle, what we'll get right now, that x dash t dash is independent also of y and z. So using the first principle, what we figured out here, that x and t is independent of y and z dash, y dash and t dash, and by applying this in frame sigma dash 2, it must be the same as all function, all physics law have same form. So we can say that x dash t dash is independent of y and z using the first principle. So this is just an error. Y dash and z dash, not t dash. This should be z dash. So this is our equation right now. This is so y dash and t dash, but from where we get x dash and t dash, we got there from here too, because y and t equals 0. So we got x dash equal a, which is a constant x, plus dt, and for t dash equal a triple dash x plus d triple dash t. So and y and z. So we substitute a and d and a triple dash d triple dash by these constants. Now we got here x dash equal sx plus epsilon t, and here y dash z dash from this from this equation, and t dash equal delta x plus eta t, which these where all of these are constant, even alpha and beta are constant. So and this is what we got when speed of light is constant. We got these before, this b, this grade b equation we got before. So right now we will prove that this s equal this eta. So let's refer back to when an event in O dash, which is an origin of frame sigma dash, always happen where x dash equal 0. So it's okay because it's happening on in the origin. So it means that it's x dash must equal 0 because we are in the origin. So, and point O dash is moving in O dash is moving in frame sigma to the right, not the left, another error. So I think these are the 3 errors I have here. This one, it should be to the right. O dash is moving to the right, as we see here. O dash is moving to the right. So from this equation, and by applying that x dash equals 0, so x dash here equals 0, this is what we get here, that Sx equal minus epsilon t, and we can say it here. So x over t, these are coordinates of O dash in sigma. We don't know actually what is the values of x and t, but we know for sure that when we divide x over t, we got v, or we can say it minus v as we minus go to. So we know that it's equal minus v for sure. Why equal why it is equal to minus v? Because as I just said, we distance over time. So this is the first one. So to the second case, when an event is happening in O, which is an origin of frame sigma, always happen where x equals 0, because we are also in the origin. So this means the event has x equals 0 because we are in the origin. Yeah. So from these two equations, x dash t dash, by applying that x here equals 0 because we are in the origin, in these two equations, we got that this equation, that x dash equal epsilon t and t dash equal eta t. So point O, which is an origin, is moving in. Point O is an origin of frame sigma, but it's moving to the left from the point of view of frame sigma dash. So just refer to Gaussian transformation and you will understand here, it. So we can differentiate here. So this is moving to the left from frame sigma dash point of view. So what we got here when we divide x dash over t dash, well, we got here that x dash over t dash must equal minus v because distance over time. Again, we don't know the values of x dash and t dash, but we know for sure that when we multiply x dash over t dash must equal to minus v, again because it goes to the opposite side. And what we got here, that so we divide both equations, that x dash over t dash and epsilon t over eta t. So x dash over t dash equal epsilon t over eta t, which is epsilon over eta, and here v we can refer, yeah, you got it, I think. So what we got here, that here we got epsilon here in the denominator and here epsilon here in the denominator. So this means that what we got here, which is s, must equal to eta. So s equal eta, and we will substitute eta by s in this equation from now on. So what we will do, we will get this equation, these 4 equations, and we will substitute it in these p equations, like when sorry for this lot of pauses, but I think you will not witness it as I pause. So whatever, what we are saying here, that we will get this equation, these four equations, and we'll substitute it in here in in the second equation. Like x dash, we get this value, which is sx plus epsilon t. We'll square it here as x dash here, so we'll substitute this and this and this and this for this second equation. And here another error, this must be t dash, not t. So I will I'll write down all of these errors and send it to you. Yeah, so this is what we got so far, the square. So when you factor this, well, you will get this term, and the same for here. Just math here or algebra. So yeah, this is what we got here. When we simplify it a little bit, this is what we got. You can actually do it your own, yeah. To understand it better, I think it's somehow reduced. So right now we need to compare coefficients of this equation with the first equation. So we need to compare this equation with the first equation of b. Yeah, this. So the coefficient of x square is 1, and the coefficient of y square is 1, z square coefficient is 1, c square, t square is 1. So, but we got here that x dash, so the coefficient here, this s square minus c square delta square, this must equal 1. And we here xt, we don't have a term called xt in this equation. There is no xt here, so this means that the coefficient of xt must equal 0. And here when talk about y square and z square, so also the coefficient of y squared and z squared is 1, and the same for c squared, t squared, so this must also equal to 1. So this means that this coefficient equal 1 for any v, yeah, for any v, and this means that when this exponential function equals to 1, so this means that alpha equals 0. So this not mean that we are considering v just when v equals 0. No, where for any value of v we get this function equal 1. So this means that this constant equals 0, and the same for beta, which is equal 0. So finally we got rid of these constants. So therefore we get that y dash equal y, yeah, finally, and z dash equal z. This is the first equation, yeah, of Lorentz transformation. Actually, you might say that was obvious, that y dash equal y and z dash equal z, because because they are working that when O on the top of O and two planes are on top of each other, and it was just obvious why we are doing all of these steps. But here just that we are. You want to prove it. You can't say it's just obvious, because as you goes the oh my god, yeah oh my god, I can't say it. Oh, okay, the consequences, yeah, it's better than Coriolis, or I think, yeah, the consequences of what we got here, what we'll get from these transformations, it will not be obvious at all. So you can't say it was obvious, yeah. You want to prove it, yeah. Okay, again for these coefficients, as we hear, this 1 and this must equal 0, because we don't have the xt term, does not exist in the first equation of b. This b equation, so there is no xt here, and same here. So we proved later that minus b equal epsilon over s, which we can say that epsilon equal minus b s. So here we got from this third equation here. We just substitute epsilon squared by this minus vs. This is what we got when we substitute. Yeah, s squared. So this means s squared over 1 equal 1 over 1 minus v squared over c squared. So this means that s equal plus and minus. Here's the point: plus and minus 1 over square root of 1 minus v to v squared over c squared. So the most famous square root in physics here. So, but what was this plus and minus? So how we will determine it is positive or negative? So because we are referring to the situation when O dash on top of O. So at this moment t equals 0, as I said. From the frame sigma point of view, actually x dash on top of x exactly agreed with each other, because here the origins are on top of each other. We are talking about this moment when O dash on top of O. So this means x dash agreed with x. So this means if there is an event having in the right of x, it must be in the right side of x dash, and if it having on the left side, it must be having on the left side of x dash. Or if it's x dash is positive, x dash if x is positive, this means x dash must be also positive. As I said, they are exactly at top of each other. So here, this is physics consideration that we are think that if this is positive, x dash also will be positive, and if this is negative, so x dash also will be negative. So we are only take the positive sign, as plus sign. So this is what s actually equal to. So s equal 1 over square root of 1 minus v squared over c squared. So when we substitute the value of the new value of s that we got right now in this equation, yeah. So this is what we will get in this equation. We just substitute it. Yes. From where we got I mean this equation, sorry. So we substitute the value of s that we got right now here, which is 1 over square root of 1 minus b squared over c squared, x plus epsilon t. So again we will go to the coefficient, another one here to got it. So epsilon equal minus v. Here epsilon equal minus vs, and we got the value of s, which is this substituted here. So this is a new epsilon, a new form of it. So and we will substitute this new epsilon in this equation that we got here, yeah. So this is what we got here, and we will take this 1 over square root of 1 minus v squared over c squared. We will get out of brackets, and here we will get, and we will name this square root is gamma. So here is gamma factor, which is the most famous square root, as I said. So this is the third equation that we got here. So here when this VC equal 0, so this means gamma factor equal 1 when v over c equal v squared over c squared or equal 1. So this means that this gamma factor equal 1. So we just get rid of this gamma, and we will get back the Galilean transformation, Actually, so here's a point that Gaussian transformation is only valid when you are moving in a very small speed. So from the second equation, this is the second coefficient on page 7. So this is coefficient. We got this is the value of s here, and this is epsilon, new form of epsilon, yeah, and here 2c square delta s, and here is the value of s equals 0. So after doing math and go to here and here, yeah, we got that delta equal this, delta equal this. So this means when we substitute this delta to the equation t dash, this equation t dash, this equation, oh my gosh, no, hold on, yeah, it's just sorry, yeah, when we consider this equation t dash, oh man, I'm kind of lost here, but yeah, t dash here equal delta, which we got the new form of delta that we got here. Yeah, we're here. So this is delta x. So, and when you refer to the equation, the a equations, so it was t dash equal delta x plus st. So, and here's delta and here's s. So when we take it outright, so we got a gamma factor again, and here's the fourth equation. So finally, these are Lorentz transformation. So here's another point to add, that we are in this proof that we are just we're not just saying that these transformations are only valid when O dash on top of O and time is equal to 0. No, this transformation or this equation are universal. So this means that it's valid for any moment, every in everywhere. So, but we are just referring to this case to know the equations, the real equations. So, but as I said, it's this valid for any moment, not just when O dash on top of O. So we are just consider it here because to get this equation, to prove this equation, yeah. So we are done here, and hopefully you understand from this freaky video that I'm present here. So, and goodbye.